working on line integrals, and that's definitely all we're going to be doing today. And we'll probably be finishing them off on Monday. So, yeah, it is what it is. We are looking at next week, because Wednesday is off, we're only looking at 4 days. And if you take into account the Tuesday that didn't happen, it means that we will be one homework off from what the schedule said it would be. But that's fine. I always factor in some spare time at the end. So that will reduce the number of questions and sections that you'll be doing in your next test. I know you've just finished one, but I'm giving you a big heads up. You've got all next week and then Monday, right? And that will be our test. So we are looking at things called line integrals. There are actually 3 stories for line integrals. Excuse me, my chair's squeaking, it's annoying me. Some line integrals are going to have a guy called ds in them. Some line integrals are going to have a dx, a dy, a dx on its own, a dxy and a dz, depending on the context. And some that you haven't seen yet are going to be line integrals of vector functions. This last one, out of the 3, is probably going to be the most practical, because this is what you typically use when you want to get what are called work done questions. So when you imagine that you have a vector field, right? So you've got in 2D space, let's say it's in 2D space, and you've got vectors pointing in various directions, and you start at one point and you travel through the vector field along a curve to an endpoint. And the work done can be found by doing this calculation. It's a line integral. That's the vector function. And that guy we've kind of already seen, but we'll show you how he works. And that's meant to be a dot product. So it's not multiplication. We'll probably be doing them at the end if we get to that, and that's fine. So I've got these guys and I've got these guys. I'm going to work on example 2s for a little while, and then I'll show you these fellas. And then depending on how much time, we'll go into the 3rd set. So here gets, let's just do them. These I can make up pretty easily. Let's do a line over C. Let's do xy plus y squared. And that guy's going to be over dx plus y squared dy. So that would be an example of this. And let's suppose I tell you that C is given already as a parametric. So in this question here, since you know that that's parametric, what we do instead is, oh, and I have to tell you a start and finish, don't I? You return everything, convert everything into t's. And then what you'll end up with in this question then is a single integral from 1 to 2 using nothing but t's. So from t equals 1 to 2, x gets replaced by 2t, y gets replaced by t take away 1, plus y squared becomes t minus 1 squared. And normally I wouldn't do it this way, but I want to just set it up slowly. Dx plus the integral from 1 to 2 y squared, which is t minus 1 squared, dy. It's very often useful to take these line integrals and split them into that guy and that guy, just for convenience. That's the only reason. Now, the reason that these are in red is that we haven't converted these guys into t's yet. So let's show you how that works. If x is 2t, then won't dx by dt be 2? And that makes dx 2 dt. And if y is t take away 1, then dy by dt is 1.
I never told her your name.
Dy is tt. Are we good with that so far? I'll just mute everybody. Go. I'll return back to here. So it's now going to be the integral from 1 to 2 of 2t squared take away 2t plus a t squared take away 2t plus a 1. And instead of dx, it's a 2 dt. And this guy is going to be the integral from 1 to 2 of t squared take away 2t plus 1. And instead of a dy, we get a dt. Can I dot this one? Would you agree it's just a horrible power rule, quadratic, evaluated at 1 and 2? Is this good? Right. Now, general truisms. A general line integral, whatever. A general line integral can be positive, it can be 0, and it can be negative. All three are possible. Now you might think, wait a minute, you told me it was the area of a curved fence, you know, and how could that be negative, and how could that be 0 even? Well, can you think of area above a curve and area below a curve? Can you think of the XY plane as being the floor? And if the curve's above it, that area will be positive. But if the curve goes below the floor, can you see that that area there, a line curve is generating an area in this case, right? Can you imagine that could be negative? So the overall effect could be positive, negative, or 0. So the rule of the game is just trust the math. If it says it's 42, great. If it says it's 0 or negative 42, equally great. Right? Okay. Are we good with this general situation? Right. Let's do one where you're not given the parametric. Let's do one where you're given a curve, and we'll keep it in 2D. Let's suppose I want to do this guy, and it's going to be xy dx. So I'm not even having a dy. That's okay. You can have that. And let's suppose I tell you that C is actually the curve y equals x squared. And it goes from the point 1, 1 to the point 3, 9. Now, the solution to this question is the same as everything. Don't we have to turn everybody into t's? The difference here is that we have to figure out how to express this curve in parametric form. If you were drawing it, it would basically be from there to there, right? So you can imagine this is the curve that we're doing this on. Right, so I have to make it parametric. We talked yesterday about how to turn things like y equals x squared into their parametric form. Can anybody tell me what that guy looks like when it's converted into t's?
X equals t squared, y equals t. Or I mean, x equals t, y equals t squared, sorry.
Agreed. Yeah. If it's a single curve, right? If it's y equals x cubed, y equals the square root of x plus 1, y equals sine squared, right? Basically, just make x, t, and y the formula, and you've got your parametric. So that bit's done. Can I do dx is dt and that dy is 2t dt? Can I do that without going through the working? Can you imagine it happening in your head? Okay. So now we've got x's and we've got the dx and dy. We are 90% finished. I know x is going to be t. I know y is going to be t squared. In this case, I don't care what that is because dt is just dx, dx is dt. One last piece to the puzzle that's missing, that's why it's 90% done. Don't we need to know where t starts and where t finishes? Agreed?
It goes from 1 to 3.
And if it's a function, it goes from x equals 1, which becomes t equals 1, to x equals 3, which becomes t equals 3. So in this case, it would be the integral of that guy, and off you go and get your answer, right? Dot, dot, dot. So we've seen one of these questions where it was given to you already in parametric form. We've seen one of these questions where the curve is described as a function of x. And the last one I want to do is just a line integral, xy dy plus xz dz over some c. And this one is 3D. And the curve C is joining P to Q. So you can imagine in 3D space, it would be starting here and going here and then having a function action on it. But you can't visualize them anymore. Don't even try. It's four-dimensional world. Your brain will hurt, right? So we just have to trust the math. So I need a parametric equation for x, y, and z. Right? Now, we get a guy called the direction vector, don't we? This is how you get the equation of a line in 3D. And the direction vector is the vector joining P to Q. And so 2 take away 1, 5 take away 2, and 1 take away 3. Are you all happy about those numbers and where I got them? 2 take away 1, 5 take away 2, 1 take away 3. Now, the general formula for these guys is x naught plus at, y naught plus bt, and z naught plus ct. Agreed? In this case, then, you typically would choose the first point, P, as your x naught, y naught, z naught. So this guy will be 1 plus 1t. The y guy will be 2 plus 3t. And the z guy will be 3, take away 2t. We all comfortable about the parametric equation of the line joining these 2 points? Straight lines are really easy to convert into dx, dy, and dz. So here goes. Would you agree that dy would be 3 dt? That dz would be negative 2 dt? And dx would be 1 dt. Are you happy about the conversion without me going through the dx by dt and then crossing over? Now you put that package together and this question's pretty much finished. X gets replaced by 1 plus t. Y gets replaced by 2 plus 3t. And dy gets replaced by 3 dt. And then the second one is xz. So x is 1 plus t. Y is, z is 3 minus 2t. And dz ends up being negative 2 dt. Okay, I just need to know the start and finish. What values of t start and finish? What will the start value, what will make you begin at p? What value of t gets you here?
0.
Right. And what value of t gets you here?
1.
Have you noticed that in the way that the equation of this line was generated, how we managed to make 0 and 1 are typically the start and finish, right? The way it was constructed. You could guess it if you wanted, but I think you'd figure that out. Can I dot that? Because it's really just another quadratic cubic power rule thing that takes 5 minutes. Agreed? Right. Not doing a lot in this one, but I want you to imagine a question that was just like this, right? Same question, right? You went from P, which was there, to Q, which is there. And then you went from Q to another guy, we'll call it R. So it's not one movement. Can you imagine it's that line, then this line? How would you adapt the process to find the complete line integral when the C is really made up of two different pieces? You know, a PQ and then a QI. How would you adapt the process to cope with that?
Well, couldn't you just do two different integrals basically and then add them together?
That's exactly what you do.
Yeah, with two different sets of limits.
Yeah. And two different parametrics, because won't the parametrics for this line not be the same parametric equation for the first line?
Yeah.
So it basically separated into two distinct questions. Find PQ, just like we did, and then imagine you had a totally new question where you found QR, and then whatever those two are, add them together and you're done. Right, as a strategy, does that make sense? Does it? How you would do it? I think there's only one question where that happened, so that's why I threw it in, because I thought yeah, it might throw you. If we're good with that, can we call this one done then, right? Okay. So this is the guy I got kind of confused yesterday and was trying to do this method on that guy. I didn't pay attention. So it's going to look like this. The main difference is this thing here called ds. So your parameters, I can't say the word. You're basically parametricizing. Yeah, I got the word, along the curve. So 1 unit, there's a variable called s and it's 1 unit. Essentially, it's x squared y, the square root of this guy squared plus that guy squared dt. So what's the big difference? The big difference is that ds gets replaced by this fella. X and y get replaced by t's, and the limits of integration, right, get replaced by t's, and c gets parametricized. So let's suppose it was this question, and they told you that x was t squared, and that y was sine t. And let's say t went from 0 to 1, right? So you are told pretty much everything that you need to know handed to you on a plate. So to find this fella, we find this fella. Well, t goes from 0 to 1. X squared becomes t squared squared. Sine t goes here. Square root of, differentiate this with respect to t, and you get 2t squared. Differentiate this with respect to t, and you get cosine t squared dt. And I'm dotting this one because, God, it's downright ugly and probably impossible to get numerically, to get algebraically, but you could always do it numerically. But I just want to do that one to kind of show you the basic process, right? That would be the integral that you'd need to find. You'd have to do some really heavy duty math if that was a real question. Thankfully, the ones that they give you to do are much easier than that. So here is our first one. It's x over y ds. Y is 2t to the 4. And x is equal to t cubed. And t goes from 1 to 4. So it's going to be the integral of x over y, the square root of that guy squared plus that guy squared dt. The integral goes from 1 to 4. X is this guy. Y is this guy. If you differentiate this guy, you get 3t squared, and then you square it. If you differentiate this guy, I believe you get 4t cubed, and then you square it. This fella becomes 1 over t. This guy becomes 9t squared. This guy becomes 16t to the 6
That should be
dt.
9t to the 4th.
Thank you. Are we good? Well cut. Okay, I'm going to try and take this one down to the point where we can solve it. Would you agree that is a horrendous integral? So let's do style points. Let's try and make it less horrendous. Is there anything you can do inside the square root? Algebraically, anything we can do to make it look pretty? Yeah.
Yeah, can't you pull out a before? And
Okay, let's do that.
Yeah.
Great.
Couldn't we
Okay.
pull a t to the 4th outside the square root by taking t to the squared?
Yep. You're right on track.
Could you also pull the 1 over t out as a natural log of t?
Oh, don't do that. No. But what I will do instead is cancel these.
You said?
Yeah, thank you. I was trying to spit it out. I was going to say, and what should we do next? Can I stop at this point? Would you agree that when you do a U-sub, you know where to go? We cool on that one? Right. I think you get 3 of these, so it's not something going to be huge. I think I'll do a circle one next and then call it good. Yeah. Only this time, it's a circle. And they mention that you go round the circle clockwise, which you might think, don't matter. Well, in this question, don't we have to parametricize? See, I said the word parametricize. This fella. When it's a circle, didn't we talk about that before? Right? And when you do a circle, and in this case it's radius 5, don't you do 5 cosine t and 5 sine t? Great. So this is going to be the integral. X is going to be turned into 5 cosine t. Y is going to be turned into 5 sine t squared. Then I'm going to have to do a derivative of ugly guy, which I don't have enough room for, dt. So I'll put it down here. So it's going to be 5 cosine t times 25 sine squared t times, no, I didn't have my formula handy, but won't it be the derivative of this guy squared plus the derivative of that guy squared? So what does that get me? Well, differentiate this and you get negative 5 sine t squared added to 5 cosine t squared dt. So this is 125 cosine t sine squared t. Okay, let's save a couple of lines of working. Won't that turn into 25 sine squared plus 25 cos squared? And what's 25 sine squared plus 25 cos squared t going to get you?
25.
And won't the square root of 25 get you 5? Are you all happy about how that just turned into a 5? So what we're now looking at is the integral of 625 cosine t sine squared t dt. And I haven't put in the limits of integration. If this is a circle and we start here, that's angle t equals 0, right? And if I go this way, won't that be t equals pi upon 2? And then if I go to here, won't that be pi? And then eventually I'll get back to here, and that is t equals 2 pi. But isn't that going from 0 anti-clockwise to 2 pi? So it would be 0 to 2 pi if I went anti-clockwise. What's the change to make it go round it the other way?
Could we just flip them?
Yeah, 2 pi to 0.
Right. Fact that at least 2 or 3 of you got that, it isn't so strange, right? It kind of makes sense. So if you're wondering what the clockwise or anti-clockwise or counterclockwise, I think is the other word to use for anti-clockwise, it just means, do you go from 0 to 2 pi or do you go from 2 pi to 0? Because one goes round, you know, the way the clock does, and the other goes the opposite to that. I'm going to leave it this way, but can we talk about how you would solve it to finish it off? What would you do to solve this?
It's a
U sub.
u sub
And who is the u sub?
sine of t.
Okay, so Calc 2 never leaves, right? I mean, it's just like Calc 1, right? Differentiation and integration are always going to be with us. That was quicker than I thought. I hope I wasn't too quick. Do you feel comfortable about what we covered? Right, then I feel good about it. So let's look at red pen. Let's look at situation 3. Line integrals that look like this. Now, these are not the same look as these. I mean, you can tell them a mile away. They don't even look like the others, right? What you're going to be given here is a vector function. So it's not x squared plus y. A vector function looks like this: x, y squared plus x, right? Or the way I don't like it, because that's just me personally, can't they also write a vector function like that? So f is going to be some given vector function, either written in this format or written in that format. Both are totally equivalent to each other. Now, C is given in terms of its vector position function from Calc 3. Remember R of t, space curve? So you might be told, for instance, that it's t squared 2t cubed minus t. Now, if you're told what it is, great. If they tell you it's a curve or a straight line, you'd have to turn it into its parametric form. So let me take that as a side issue. If you were told C was x squared plus y squared equals 25, right? Then wouldn't x be 5 cosine t and wouldn't y be 5 sine t? Right, that's parametric. In the space curve world, all you do is you take these guys and you put them inside a space curve. So they're really equivalent, aren't they? Parametric, space curve, right? So back to this fella. You need a start and finish, right? A t value to start and finish. So let's say from 1 to 2, right? Typically you'd be given that. So what does this guy look like? Well, he is this fella, dot r dashed of t dt. So you take the dot product of these two, right? This guy and this guy, the dot product. Oh, by the way, not this guy, but the derivative of this guy. And then you slap a dt at the end. So let's find r dash t. From Calc 3, are we happy with the derivative function r dash of t? Okay, now I'm ready to put the pieces together. This fella here. It's going to be the integral from t equals 1 to 2. The space curve is this fella, and I'm going to do it kind of slowly. Dot product with r dashed of t dt. So I'm kind of mixing and matching things right now. That's integral from 1 to 2. R dashed is 2t, 6t squared minus 1 dt. Oh, wait a minute here. What do you think I'm going to do with x, y, and with y squared plus x? I'm not going to keep them as x's and y's, right? I'm going to turn them into t's. And won't I use that that's essentially who x is, and that's essentially who y is? So the first fella says x, y, and that becomes t squared 2t cubed take away t. And the second one is y squared, which is this guy, 2t cubed take away t cubed. Plus x plus a t squared. So let's keep going with this. It's integral from 1 to 2. I'll multiply this out, so it's what? 2t to the 5 take away t cubed. Oh God, I wish I hadn't done this question now. 2, 4, 8. 8t to the 9. If you multiply them together, you get 3, and you get a negative, and you square that. So you get 4t to the 7, 12t to the 7 with a minus. You're going to have to trust me on this if I screw up. pretend I got it right. That guy gets your square, and you're going to get 3 of them, so you're getting 6t to the 5. That guy will get you a t cubed, and then a t squared. Dot product with this fella and that guy, dt. Okay, I'm ready to dot this thing. Won't you basically do the integral from 1 to 2 of 2t times this guy plus this mess, which is 6t squared minus 1, times that fella, dt. I should have just picked one of the questions, because I'm sure it would have been much smaller. But then I would have used up a homework question that you didn't have a new one to see. All right, that is really ugly, but can you imagine that the process won't be changed? They just get ridiculously big. So I'm going to pick one now. Probably should have done it the first time. But I
You
keep
want us to say
having
hi
the...
in chat?
Sorry, I got a question in chat. Okay, let me see what that is.
I said, do you want us to say hi?
Oh, why not? Yeah, do that. Give me a chance to look up a good question. I was going to say I'm an optimist, and I keep thinking that I'm going to be able to make a question that comes out nice. And every time I do it, doesn't it just end up big and ugly? So, learning from that mistake, this is a homework question. And we're being asked to do that guy. And the vector function is 3-dimensional. And it's x plus y squared, xz, and y plus z. I'm not actually convinced this is going to be any nicer than the one I just did. R of t is t squared, t cubed, negative 2t, and t goes from 0 to 2. And maybe I'll get lucky. I'll hold back a little bit before I say this is going to be worse than the one I did. Don't we need to find r dash t, because that's part of the thing that we need? Well, the derivative of this guy, I guess that is nicer. It's 2t, 3t squared, and the number negative 2. So the line curve FDR is the integral from 0 to 2. The dot product of x plus y squared, xz, y plus z, dot product with the derivative function dt. So it's going to be the integral from 0 to 2. X gets replaced by t squared, y gets replaced by that guy because you square it, comma, xz gets replaced by that guy, and y plus z gets replaced by that guy. And the dot product was 2t, 3t squared, negative 2 dt. Right, remind you how dot products go. X gets multiplied by x. So if you take this and multiply it by 2t, you'll get 2t cubed plus 2t to the 7. If you then take the y, you multiply the y's together, you get negative t squared times that, which I believe is negative 6t to the 4. And then you take this fella, and you do it with negative 2, and you get negative 2 cubed plus 4t dt. Are we comfortable about what I just did mostly in my head? And secondly, did I do it right? That guy times 2t,
I think
the
that
middle guy,
negative 2t squared should be a negative 2t cubed.
whereabouts is that one? This one here?
In the middle, up top. In
Yep.
the right before the dot product.
6t to the fourth should be 6t to the fifth, not
6t to the fourth. This one here should
Yeah,
be
that's what
6t to the 5.
yep.
Are we good now? Okay. Is there any collecting? Well, there is some collection, so I should do it. Won't that guy get killed off by that guy? Power rule, add 1 to the power, divide by the new power. Add 1 to the power, divide by new power. Power rule again. Evaluated at t equals 0, t equals 2. 2 goes into that, 2, 2, 2, 4, 8, 16, 32, 64. 2, 4, 8, 16, 32, 64. Oh. And it's the right answer. It's 8. Now, this particular line curve has a different meaning than the area of the bent wire, right? Which is what the others were kind of trying to visualize or explain. I want you to imagine, and this is going to just be a 2D version of the same situation, that we have, oops. So this guy is your vector function, right? And you have a curve C that might start here and end up here, right? And you travel along it in that direction. And that's your curve C. When you evaluate the integral, the line integral along the curve C of this fella with respect to that guy, what you're calculating is the work done in passing through a vector field. Now, that vector field could represent almost any kind of field that you could come across. Couldn't it be a magnetic field? And this is the pathway of a small ball bearing traveling through a magnetic field. And how much work would be done in going from here, traveling along that curve and getting to here. And the work done could be 0, it could be positive, or it could be negative.